Hello guys. Today, last class we were discussing axial shear and moment diagram for frames, and today we are going to be focusing on trusses, introduction to trusses. This is the first part is like a review for statics, and I have in modules, and I have also in the YouTube channel. I have that material over there, but let's just review it a little bit for your convenience. So what is a truss? The basic definition of a truss is that the truss is a structure composed of slender members joined together at their endpoints. This is the most basic definition that you can find regarding a truss. What do you get from here? You get from here that they are slender, has to be a slender member, so these members have to be slender. Slender meaning the cross-sectional area is small compared with the length. That's what a slender member means, basically. And they have to be connected at their endpoints. Now, if a truss and all the loads are in the same plane, then we're going to talk about planar trusses. Otherwise, we will be talking about 3D trusses. The basics, once again, simplest truss start with 3 members connected by 3 joints, and if you want to keep making it, this is a simple truss. If you want to keep making it bigger, you just have to add 2 members and 1 joint in the direction that you need to add those. Why not rectangles? Well, this is explained also in the statics review, but if this is a triangle, the structure is stable. If this is a rectangle, it's a mechanism with too many degrees of kinematic freedom, and it's not stable in that case. Now, there are certain assumptions and rules that have to be happening in order for a truss to behave like a truss. I always say things like you can see something and you can swear it's a truss. It can taste like a truss. You can be 100% certain that it's a truss, but it's not a truss, because for a truss to behave like a truss, these assumptions and rules have to be kept. The first rule is this: all loads are applied at the joints. Now, the self weight or the distributed weight of the member itself is impossible to be applied at the joints. It's impossible because it's a distributed weight. But however, this member weight is so small in comparison with all the external loads that it's not that you neglect the force and say, oh, this weight doesn't exist. It's that you say, oh, I know this is a distributed load. I know it's acting in the member. However, what I'm going to do is I'm not going to neglect the weight of the truss because it's too big. You can have 2 tons, 3 tons, 4 tons, and more trusses, weight of trusses. But what we are going to do is that we are going to assume, there are several assumptions there. One of the things that you can do is that the total weight of the member, you say, oh, I'm going to place the member here, the member weight here at this joint, and the member weight here at the other joint. Or you can get the total weight of the truss and distribute it either in the top chord or the bottom chord or in every single joint. But the external loads have to be applied only and only at the joints. Now, let's imagine that this is just, I don't know, a warehouse that you are building, and this is one of the parts. You have the truss here, you have the columns, and in the other side you do the same thing, and you put the cover of the roof here. And I always ask, what is the main load acting on this thing? And people say, oh, the weight of the cover, the weight of the truss, or whatever. No, it's the wind, or the snow, or whatever other word. But if you are here, probably it's going to be the wind. So if the wind is blowing here on this deck, it's not acting at the joints, it's acting everywhere. The wind, right? The pressure of the wind. So this is going to make this member that is really slender, like this, deflect really easy. And then the structure is going to fail by instability, and it's not going to fail by the load. So how do you achieve in real life that all the loads are applied at the joints? In the case of that example, what usually is done is that between truss and truss at the joint, wherever the joints are, you connect these members and these members are called purlins. They go exactly on top of the joint, and then on top of those purlins you put the cover, you put the roof. What happens here is the roof transmit the loads to the purlins, and the purlins transmit the load exactly to the joints. So the first rule, got it, done. Now the second rule is the members are joined together by smooth pins. Smooth pins means you're gonna have here a pin that is gonna make these rotate freely. Basically, that's what it is. Now, can you tell me if this is a pin? None of them looks like a pin. This might look like a pin, more like a rusted pin than a pin, but yes, might look like a pin. But this is not a pin. This is not a pin. This is not a pin. Definitely not a pin. However, they behave like a pin, not like a smooth pin, but they behave like a pin because they allow some rotation to happen. And usually people fail into identifying the rotation. They think that the rotation is something that you just get the element and it's like, oh, freely rotating everywhere. No, the rotation is measured in hundreds of degrees, tens of degrees, and it's really small. So if you realize these type of structures, if you have any load here, this is going to be able to rotate. So we can live with that. And on top of that, remember all the considerations that we have with the loads, and we explained that in previous chapters. The loads are factored, the capacities are reduced. So yes, we can live with these as pins. Why don't we build those? Why don't we build those as pins? Well, because building perfect pins will be impractical and extremely expensive. And these, for our purposes, will behave like a pin. So if we comply with those assumptions, plus we get the self-weight and redistribute it, then this is the beautiful thing about trusses. Because now all the forces, all the internal forces in the members are going to be only in tension and compression. That's it. Tension and compression. Now, the steel is a majority of the trusses are made out of the steel, for not necessarily, but steel. And I always explain this, like if you have a steel that is 60 ksi or 65 ksi, and you have a cross-sectional area of 1 by 1, that means that little bar can take 60,000 pounds of force, which is a lot. Now, usually, and you know that it's not the same thing in tension than in compression. Now, when the members are in compression, usually these members are thicker because when I'm pressuring these, the member is going to buckle in different modes, but it can buckle. And if the member buckles, it's going to become unstable. So usually the members in compression are thicker in the trusses just to prevent that buckling. Or we have auxiliary members that we're going to explain later as zero force members. Now there are hundreds of types of trusses for roofs, and the selection depends on the characteristics of the construction that you are doing and what is your main objective, what is your main goal for that roof. If you're looking for clearance here, maybe you are going to go with a scissor, but if you have a big span, moderate span, then you might go with a Pratt or a Howe truss. And if you have a really large span, maybe you can have a Fink or a fan. I mean, I'm telling you, there are tons of trusses and everywhere. And our objective is not to do that right now. Our objective is just to introduce trusses and design trusses. This is more related to projects, and you will learn that later on probably in your career. You have also bridge trusses, and as you can imagine, it's not one only truss. It has to be two parallel trusses, and usually you have two connected in a single span. You can have multiple spans, but they are not continuous. They are single spans. And what you can have cantilever trusses also, but then the cars are or the vehicles are circulating here. So if we want the loads to be transmitted to the joints, basically what happens is that the car goes on top of the deck transmits the load to the stringers, which are these members, and those stringers transmit the load to the floor beams, which go in the other direction, and the floor beams transmit the load directly to the joints of the parallel trusses. That's what is happening there. Now the trusses have to be also connected. You see these connections here and these diagonal connections there. Those connections are for sway, so to prevent sideways in the trusses. And there are different type of bridge trusses also. This is just here as a reference for short spans. Usually people use Warren trusses, and for larger spans you can use Parker trusses. That doesn't mean that you have to now. You can imagine that, for example, this arch type of a structure will help with longer distances. Classification of trusses. Well, we already mentioned one of the trusses, a simple truss. Simple truss, 3 members. If you are in 2D, 3 members connected by 3 joints. That's it, nothing else. Now you have compound trusses also, and there are different type of compound trusses. Compound trusses are, for example, several trusses connected by a common joint, or trusses connected by 3 bars, several trusses, or trusses joints with many bars, different type of bars, or one of the bars is replaced by trusses. Let me explain you that. This is one case, this is another case, and this is another case. So if you have this case, for example, the first case, simple trusses connected by a common joint, it could be something as simple as this. This is a simple truss, and this is a simple truss. You get both of them, you connect it there at one joint, and add 1 bar. That's it. And then you have that type of compound trusses. Usually you can solve these by making a cut here and studying one side of the truss. Usually, not necessarily. Then you can have also simple trusses joined by 3 bars. You have truss, you have a truss, you connect the trusses. There you go, compound trusses. Now be careful, because if these 3 bars are concurrent, you might have instability in that truss, and we're going to define instability in some minutes. Now you have another type of compound trusses, which you can have several members of these bars replaced by trusses, something like that. And we have here at the place where I teach at UCF, we have here several cases, or we have a very small, very good example of those. And this is the steel bridge that the university uses for the steel bridge competition. You can see that these elements here, these bars, have been replaced by trusses. So whenever you have a time, go and take a look at the bridge. It's a really nice example. And then you have complex trusses. Complex trusses are those trusses that cannot be classified as simple or compound, and they cannot be calculated with the static equations of equilibrium. Now a truss can be in the same way that the beams, trusses can be determinate, indeterminate, or unstable, and they can be determined internally or externally. So we can determine how a truss is stable or determinate by counting reactions and counting forces. That's basically internal forces I'm talking about. So if you have the number of bars plus the number of reactions is equal than 2 times the number of joints, the truss the 2D truss is statically determinate. If it's bigger, then it's going to be statically indeterminate. And if it's smaller, it's going to be unstable. Now, what is the logic of this? When you are going to analyze, or I don't know, try to calculate the truss, every bar is one of the unknowns that you have, the internal forces in tension or compression. So those are unknowns. And also the supports, wherever this is a support here and here, those supports are also unknowns. You don't know them. So these left hand are the unknowns. And per every joint, if you use the method of the joint, for example, per every joint, you're going to have two equations that you can use. Summation of forces in X, summation of forces in Y. So this is the other thing, that the number of unknowns and the number of equations. So if the number of unknowns is equal to the number of equations, bingo, you can do it. If the number of unknowns is bigger than the number of equations, you cannot solve it in statics, or you cannot solve it using a static equation of equilibrium. It's not that you cannot do it, it's that you just cannot do it using static equations of equilibrium. You have to go to other methods for solving indeterminate structures, like a force method, I don't know, consistent deformations, for example, a stiffness method, and so on. And the degree of indeterminacy is just subtracting the number of unknowns minus the number of equations. That's basically it. This is what I was telling you about unstability. If the number of unknowns is smaller than the number of equations, then the structure might be or will be unstable. In this case, don't look at it from the mathematical point of view, because you can see also here that the system of equations is unstable. But look at this for the point of view. So you're gonna have more forces, internal forces, acting or happening in the structure than the number of resistive possibilities for that truss. So what is going to happen is that it's going to move in some direction. That's what's going to happen. It's going to be able to move in some direction, so it's unstable. And then you have external stability and internal stability. However, for this class, I would like to talk about just internal stability, or just stability or instability as one, not as two. But for you, so you have a little bit more background, you can have something that is external stable, however, is internal unstable, or vice versa. For example, if the number of external reactions is equal to the number of external equations, summation of forces X and moment, now I'm talking about in 2D, in rigid body, then that will be determinate. But what happens if those reactions are concurrent? And we learned that even for beams also, that happens for beams, not only for trusses. This is the example. You see, you have three reactions. Internally, you see that truss and you say, well, that truss is stable, I don't have any problem. However, when you realize the three reactions are concurrent, this is your key, concurrent reactions. And when the three reactions are concurrent, that truss is going to be unstable. Now, if you just look at the truss over there, if you apply a load here, any load, even the self-weight, this is a roller, so this is gonna slide, and because this is a pin, it's gonna collapse. So that's unstable. Another example of external instability is when you have parallel reactions, and we discussed that in other courses also. Why is this? Well, under vertical conditions, this is stable. Apply a horizontal load or an inclined load, and it's going to be able to move in that direction, meaning is unstable. Keyword, parallel reactions. All of them. Keyword, concurrent reactions. Now, when you talk about internal stability, this shape has to be maintained to be stable. Now, this is stable because it behaves like a rigid body. Now, look at this part. You don't have any fixicity provided between these joints, meaning that's going to be unstable. This is by inspection. You can see them by inspection. This is what I was telling you. You have a compound truss here, and now the three bars are concurrent in that point. Yes, it's true. You are joining two trusses with three bars, and that classify that as a compound truss. But because these three bars are concurrent at that point, that truss is going to be unstable, and it's going to be more like a mechanism instead of a truss. So how do we how can we mathematically determine this? This is just a summary of what we discussed. If the number of bars plus the number of reactions is smaller than 2 times the number of joint, unstable. If the number of reactions is bigger, number of reaction plus bar is bigger or equal than the number of joint, it's gonna be unstable only by inspection. You can see it if the reactions are concurrent or parallel. Let's check these examples to see how do you do. And I put here the equations. For this truss, we have to count and classify as statically determinate, indeterminate, or unstable. So we have to count the number of bars, the number of reactions, and the number of joints. So here, how many bars? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Perfect. You have 13 bars. You have 3 reactions, 1, 2, and 3. And you have 1, 2, 3, 4, 5, 6, 7, 8 joints. This is what you have. Number of bars plus reactions, 16. Number of joints, 8. 8 times 2, 16. So because this happens, that structure is statically determinate. Well, let's look at this one. I can see it. I don't know if you see it, but I can even see that just by looking at that. You see there's no fixicity here, so that's going to be unstable. But let's see if the equations determine the instability. Number of bars. How many bars? You have 1. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 bars you have. And reactions, 2 plus 1, 3. How many joints? 1, 2, 3, 4, 5, 6, 7, 8 joints. Bars plus reaction, 15. 2 times the number of joint, 16. So that structure will be unstable, as we predicted just by inspection. Next, I can see that, and you will see that later on. Just by looking at that truss over there, I can see that that truss is indeterminate. You can see it. It's obvious. But in case that because this is not the joint here, okay? So basically in these triangles, if you want to call it like that, have an extra member. But anyway, if you count the number of bars, it's 11. The number of reactions, once again, is 3. Number of joints is 6. Therefore, you're going to have 14 unknowns, 12 equations, and 14 minus 2 means that this is going to be statically indeterminate of second degree. And this one, I don't even have to do it, and you don't even have to do it. Look at this. Any load that you apply here, this is going to slide because there's nothing holding it here. How do you make this stable? Putting a bar there. But for the time being, that's unstable. Okay, now, that was 2D trusses. Same principle applies to space trusses, like these ones. Same thing. It's a different animal, but it's the same thing. Now, the 2D trusses are, the simple trusses start with a triangle, 3 bars, and 3 joints. Now, an elementary space truss or a simple space truss consists by 6 members and 4 joints. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And they connected in a form that is called a tetrahedron. Now, you wanna make it more, you're gonna make a bigger space truss. What you do is that you just add 3 new members. In the other case was 2 members and 1 joint. In this case, we add 3 members and 1 joint. So that was our original truss. We add 3 members and 1 joint, and we say 1, 2, 3 with that joint, and then you say 1, 2, 3 and another joint, and then you form the new truss. 1, 2, 3 and 1 joint, and you have the previous one, which was this tetrahedron here. 1, 2, 3 and 1 joint. You want to add another one, you put here 1, 2, 3 with the joint over there, and you keep making it bigger and bigger and bigger. Now, if you apply the same principle that I discussed before regarding the number of equations and the number of unknowns, well, here the number of bars plus reactions are the number of unknowns, but in every joint, because it's 3D, now I have 3 equations, summation of forces in X, Y, and Z. So this is going to determine if the structure is statically determinate, indeterminate, or unstable. In the same classification that we had before, simple trusses, tetrahedron, and you just add 3 members and a joint. Compound trusses, you have 2 different trusses, and you add the 2 trusses by adding a certain amount of members and connected at the joint. And complex trusses, those are the ones that are not classified as simple or compound, and that goes beyond the extent and the content of this class. Determinacy and instability, in the same way that we do it internally, we can do it in 2D. Now we can do it here also for 3D. If you're talking about in external stability or instability, number of reactions, now is 6, the number of equations. Why 6? Because we are in 3D, so we have X, Y. When you do the external reactions, remember you did the whole truss as a rigid body, and then you're going to have summation of forces in X, Y, and Z, and summation of moments in X, Y, and Z. That's what you have. Now, for internal determinacy or indeterminacy or instability, the same concept apply. You have 3 forces, 3 equations per joint, X, Y, and Z, and you have the number of bars plus the number of reactions as your unknowns. Depending on these numbers, the truss will be stable or unstable. Type of supports. The type of supports for 2D trusses are similar to those on 3D trusses. You have this short link that will be only one force in that direction. It says here a slotted roller constrained in a cylinder. I don't care what is the name. I care how this move. I know this, if I try to pull this bar up and down, I'm not going to be able to do it. So that's why I have that reaction over there. I can slide it in this direction. That's the idea of that slotted roller there. But I cannot do it in this direction, so I have 2 over there. Ball and socket is one of the most common types. Ball and socket is just 3 forces and no moment in any direction. And the roller is the same in 2D as 3D. You don't have fixed supports here, of course, because if it's a truss, you cannot have moments at the joints. Otherwise, it wouldn't be a truss. Example. How do you classify these as determinate or indeterminate or unstable? Let's see. All the 3 supports are ball and socket. Ball and socket means 1, 2, 3. 3 reactions. So the number of reactions here are 9. 3, 6, 9. The number of bars, 1, 2, 3. And the number of joints, 1, 2, 3, 4. What is the equation? The equation is the number of bars plus reactions, my unknowns, bars plus reactions, has to be equal to the 3 times the number of joints, which is the number of equations that I have. And because they are the same, this is a statically determinate truss. What about here? There's a bunch of things here. How many reactions? 1, 2, 3, 4, 5 times 3, 15. 15 reactions. How many joints? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many bars? A bunch. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 1, 2, 3, 4, 5, 15. So what is the equation? Number of bars plus reactions has to be equal to 3 times the number of joints. 15 plus 15 is 30. 3 times J is 30. Statically determinate truss. This one, I don't know about you, but I already saw it. But count. How many bars? How many reactions? 3, 6, 9, 12. And I'm not going to count the bars or the joints. I have them here. So you have 12 reactions because those are ball and sockets. 12 reactions, 8 joints, 13 bars. Bars plus reactions, 25. 3 times joins 24. That means that it's statically indeterminate of first degree. And so on. You keep applying the same equations. I don't want to make the lectures longer, so long, so I'm trying to cut them to the minimum that I can. So for the next lecture, we're going to be discussing zero force members and how to solve 3D. I have several study sets already in modules, and I have several videos also in YouTube that you can go and you can watch. See you later, guys. Have a good day.